3D space is represented with the x, y and z axes, and together in Maya they form what's called a right-handed coordinate system. So if we take a look at this model here, which is a right hand, the x position will be your thumb, and the index will point at right angles and will point in the direction of the y-axis, and this your second finger will represent the z-axis. So if we look in the front view in Maya, the z-axis is not visible as it is coming out of the screen towards us. The positive x direction is to the right, and the upwards vertically is the y-axis. The Cartesian coordinate system is used to define many properties of a 3D object, including its position, rotation and scale, and we used ordered triplets to identify points in space. So if we move over to our script editor here, we can create a cube. A cube is made up of bases, edges and vertices, and we can query this here using this script. We can see the number of vertices is 8, bases 6, and edges is 12, and we have this nice Euler's rule which states that the number of vertices and plus bases should be equal to the edges plus 2. So we can run this to verify this, and we see that evaluates to true. Each polygon is represented in Maya by a list of related coordinates. So if we run this function here, we can query the polygon and get back a list of all the vertices contained within the cube. You can see the first point here is -2, -2, 2, correlates with this point here. So if we do translation along the x-axis and run our function again, you can see we've moved 7 along the x-axis. We can also select vertices, so we'll select the same vertex, move it out in the z direction, and run this script again. You can see we've moved it up 5 on the z plane. We can get the cube's current position. At the pivot point we can see that it's at 7 on the x, 0 on the y and 0 on the z. We can query this cube's scale. We can see it's at unity scale 111. So if we scale it out, some factor, and run the script again, you see our values in decimal. We can do rotation. We can query the query the cube's rotation. Do some rotation. Z, X, Y. You see we get back values in degrees of -41 on the x, -23 on the y, and -19 on the z.
So now if we take a look at vector addition and vector subtraction, we need two vectors here. Vector A with its tail position at 0, 0, 0 and its head position at -4, -5, 4, -9. For vector B, its tail is also at the origin and its head is 4, 3, -5. The first thing we would need to do in the case they weren't position vectors is get the components for each, and we do this by taking the tail from the head, which should give us back these results: -5, 4, -9 for A, and 4, 3, -5 for B. So the convention for vector addition here is to add up each of the vector's corresponding components. So, and that will give us a vector C. So if we add b plus a, and we'll get c, it's minus 1, 7, minus 14. If we do a plus b, and should give us minus 1, 7, minus 14. And this tells us that vector addition is commutative. So now we can plot the points for vector c with this locator, this code here, and it should move it to the points of vector c that we have found here. Now if we take a duplicate of vector b and move its tail, will start at a's terminal point. So if we run this code here, it duplicates it, and you can see they have the same direction and the same magnitude. They're basically the same vector. So to find vector c, we can figure out this resultant vector by going from the initial point of a to the terminal point of b. So that's basically what this code here is doing. It will give us vector c. And now we can delete this. So now if we take a look at vector subtraction, first we look at b minus a, and it will give us a resultant vector d at the point 9, minus 1, 4. So if we look at a minus b, that will give us the vector minus 9, 1, minus 4. So this shows us that vector subtraction is not commutative, and these vectors, although they have the same magnitude, they're going in opposite directions, so they're not the same vector. So if we take a look at a minus b here, we can just run that again, and we can plot for the vector d, and will give us this point here. So if we walk along the vector a to this point here, its terminal point, and it should give us the vector from here minus b. This vector, it'll have the same magnitude as b, but will go in opposite directions. So in this line here, we have to change its pivot point to denote its tail. So we just run that code. It gives us this. If we start at the tail of a here and we go along to minus the head of minus b here, we should get the vector d. If we run this, this is the vector d. So now we can delete this duplicate. Every non-zero vector has a corresponding unit vector that has the same direction, but with the magnitude of 1. So in order to get the unit vector, the first thing we need to do is find its components. So in this case, we have a position vector from the origin to, and if we get the point at the end, it should work out as 3, 4, and 5, x, y, and z. If we draw 3 along the x-axis, 5 along the z-axis here, and if we go up 4, we should end up with a right angle triangle, and the magnitude of the vector will be equal to the hypotenuse of this triangle, so we can use the Pythagorean theorem to calculate it. So to get the norm or, get the square of each of the components and get the square root of that, and that will work out as the square root of 50, which in turn is the square root of 2 by 25, which will lead us to 5 multiplied by the square root of 2. And that's what this line here is basically doing. It's multiplying each component by itself, which is a square, and then using the maths function and getting the square root, which will be referenced by our variable n here, which works out at this decimal number. float. In order to find the unit vector here, we divide the vector components by the magnitude. The formula uses scalar multiplication, as the numerator is a vector and the denominator is a scalar. And so if we do that and save it into this variable u, we can find it as these values here, and we can plot u using this and see our unit vector. To verify that it's a unit vector, we can find the magnitude of it by using the Pythagorean theorem again. So if we just run the same code we used and print this, we should get 1.
So a unit vector is simply a vector of unit length with the same direction as a given vector. This simplifies operations involving only magnitude and direction by taking the norm, and can in turn help ease computation for 3D graphics processing.
So now we're going to take a look at how to get the length of a vector. The vector doesn't have a unique position in space, so what I've drawn is just a random line here to represent the vector, with this vertex here denoting the head, this one here representing the tail. So if we move into the script editor, we can query this vector and print the tail position. For the x, y, and z is 2, 3, 0. We can do the same for the head. The position on x, y, and z for the head is 9, 8, and 6. Given these coordinates of the head and tail, we can find its components for delta x, delta y, and delta z. To do this, we take each of the x, y, and z tail positions and minus them from the respective x, y, and z head positions. So that's basically what this line here is doing. For each index position of the tail, it's taking it away from the head and giving us delta x, y, and z into this components here, component list. So if we run that and print it, we can find the components as 7, 5, and 6. From there, in order to get the magnitude, we have to apply the Pythagoras theorem to the components. So if we were to consider this vector here, we can do that down here by multiplying each component by itself. Basically, that's given us this square of each component of delta x, delta y, and delta z, and then we pass it to this the square root, this maths function, and that should give us our magnitude. So if we print that, it works out at 10.488, and we can verify that if we take our components once again, get the square root of 7 plus 5 squared plus 6 squared. That should give us 10.488.
The dot product is the product of each of vectors' corresponding components added together, and the result will give us a scalar value. So if we can use the dot product to find the angle between two vectors. We can take 2 points, and we can use these to represent vectors O and S. There are two ways to calculate the dot product. First involves multiplying the magnitude of R by the magnitude of S and multiplying that by the cos of the angle. And the second one involves the product of each of the vectors' corresponding components added. Basically, that's what this line is doing here. It's getting the corresponding component, the product of the corresponding components, adding it together, giving us the value. That equals 32. So if we get the use Pythagoras theorem to get the magnitude of R and S, we'll do this by multiplying each of the components by themselves, squaring them, passing them to the square maths function. We get two values, and from this we can deduce the angle between the two vectors using this formula. It's the cos of beta is equal to dot product divided by the magnitude of R multiplied by the magnitude of S. So if we look, that's what this is doing here, using the arc cos and passing these the values we've got previously into it and converting it to degrees and saving it into this variable. So if we run this, we should get the angle. Actually, it equals rounded to 1 decimal place, 62.1.
We can also use the dot product for lighting calculations. If we consider a light source at 4 on the x, 4 on the y and 8 in the z direction, and an illumination point at 0, 1, 0. Lambert's law states that the intensity of the light on the diffuse surface will be proportional to the cosine of the normal vector and the light source direction. To begin with, we get the normal to the surface. The direction of the light source from the surface is defined by the vector s. So we get that. And then we need to get the magnitude of both S and N, and using the second part of this formula here, we can find the product of each of the corresponding components, and that will equate to 3. And using the first part of this formula, we can find the cosine of the angle is the product over the magnitude of S, and that will give us a light intensity of 0.3179 times the intensity of the original light source.
We can use a cross product to calculate the normal to the surface, and the result will be a vector at right angles to the surface. So if we define 3 points here and set up 3 locators, 3 points V1, V2, V3. We draw a plane between these points. And we can use this M vector class to wrap our vector points into a vector object. So we're using this class and using these operators here to, that's an easy way to get the components. And we can print, we can see our components. Formula for the cross product is the magnitude of R by the magnitude of S by the sine of the angle between the two vectors, and the n here is the unit vector at right angles to both R and S. So if we take the cross product of v1 minus v3, v1 minus v2, so this vector is R, and v2 minus v3 is this vector is S along this line here. We can also get the cross product by getting the determinants. So this is what this formula is here, by using the Cartesian unit vectors I, j, and k. We can get for I, we can ignore the first row, which are the x values in this case, and we multiply, we cross ry with sz minus rz minus sy. For the j, we ignore the second row and we can cross rx by sz minus rz by sx. And for the k, we can ignore the third row, which will be the z values, and be Rx by Sy minus Ry by Xz. So if we run this here, and this operand here is part of this class, that is an easy way to get the cross product. So we can do it that way too. So if we run both print out all our values here, you can see that we get the same values for both. So we know that this formula here is working. Okay, to calculate the normal to a surface, then we have to get the normal of the cross product and add it to the point at which we want the normal to the surface. So if we run this on this, we should get a line here that's at right angles to both R and S. So the normal of the vector t, in this case this line, is derived from the cross product of R cross S. We can figure out the direction visually using the right hand rule. So if you align your thumb to R here and your index finger to S, your middle finger should point in this direction here. These points are anti-clockwise, so that looks like the right direction. As a demonstration on visualizing matrices, I've set up a function here that's called update polygon, and contains a transform matrix. The variables in here will pertain to x, y, and z and the homogeneous coordinates, and values will get passed. These values will get passed into the function, and depending on the type of transformation, they can change. So, for instance, the translate, if we're using these formulas here, this formula is a translate formula. The h1, h2, h3 values will update, while x1, y2, and z3 will remain constant. For scaling, we're using this formula here. It's for the arbitrary point, and the h1 and h2, h3 values update with the points that are passed in through this variable scale p, and if that's not passed in, then it will take the default values here. This default matrix is the identity matrix for rotations, and for rotate we are using these three matrices, and basically we're getting the cos and sine of the angle passed, leaving h1, h2 and h3 at 0. For scaling on the x-axis, we can change the x2 to a minus, or the z2 to a sine, to a minus sign, and the same we'd do the same for y and z if those values are passed. At the end of our update polygon function, then we have the vector multiplication, and we're using 3 for loops for this. The outermost loop we iterate for the range of the vertex list that we take from the cube. The middle loop here, we will iterate 4 times for each x, y, z and homogeneous coordinate of items in the vertex list, and we're initializing this coordinate here each time. And the innermost loop here will multiply 4 coordinates by each row in our transformation matrix and add them to the coordinate variable, and this in turn will update our result matrix and will translate our cube or transform our cube, and then we'll center the pivot, and then we can see the result matrix. So we can now go ahead and run the script. We have a polygon, initialize a vertex list, and this is for holding the current vertices of the cube. This is an initialize function that builds the polycube and aligns it to the x, y and z planes. This is a function to count the vertices on the polygon. This function will center the pivot after each transformation. This one here will query the cube vertices and add to the vertex list, and it also appends a homogeneous coordinate that will allow vector operations to be represented as a matrix by which the vector will be multiplied. We can initialize that. So if we run our initialize function, we should get a cube. So once we have all our script compiled, we can go ahead and test. First of all, we can test for translate. We've set up a locator here at 666. So if we update polygon with type translate, the value is at 666. We should translate to this point. So if we take a look up here at a vertex list, the original first point here was 0, 0, 4. That should have given us back a 4 by 1 matrix, and 6, 6, 10 is now the new vertex point. So next we could take a look at scaling. So I'm going to scale in a factor of 2 in all directions. I'm passing this point here by which to scale by. It's the -1, -1, -1, and I pass the type scale. So if we run this, we should see that it's scaling to the point 1, 1 each time. We can also specify a different point. So I'll center the pivot there again and pass that as the point by which to scale. Run this again, you can see it's now centering in the center. Next we can take a look at rotations. So if we set our type to rotate, angle to 45 degrees, and axis to Y, we can move into our top view. On this, it should rotate about the Y axis, and you can see the result matrix from our transforms. We change it to Z-axis, move into the front view. We should rotate around the Z-axis, change the angle, and finally the X-axis. We can translate beforehand. We should rotate around the X-axis at 90 degrees each time.